Hello, everyone. Welcome to today's webinar. I'm Alex Taylor, a contributing editor to CNEN Media Group. I'll be moderating today's event, a collaborative approach to the development of a byproduct removal strategy and a successful transfer to pilot plant. This educational webinar is sponsored by Cambrex. Cambrex is a global CDMO that develops and manufactures drug substances across the entire life cycle. CNEN works with sponsors to identify topics of interest and value to CNEN's audience and consistent with CNEN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the help widget at the top right corner of the screen or type your query into the Q&A box. If you're disconnected during the webcast, please log in again according to the instructions that you received earlier. You're encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will pose as many as time permits. This webcast allows certification of participation. Please click on the certificate icon below your Q&A box to download your certificate after watching the webinar. Please note that CNEN does not endorse any company, products, or services that may be mentioned in the webinars. Each webinar will be archived at CNEN online after the live webcast. During the presentation, we will hear from Jenna Humke, a senior scientist at Cambrex, and Mark Stevens, an engineering fellow at Cambrex. Now let's get started. I'll turn it over to Jenna.
Yes, thank you for that introduction, Alex. Thank you to everyone for tuning in. We're excited to kind of share what we've been working on here at Charles City. So to give you a little overview of Cambrex, like Alex said, we are a CDMO with sites globally. We're headquartered in New Jersey, but we have several sites in North America, as well as in Europe. And so each site has a range of capabilities from early stage to late stage and commercial manufacturing. And we also each has kind of knowledge on enabling technologies such as continuous flow, biocatalytic reactions, as well as skills with controlled substances and high potency. So with our Charles City site, which is where me and Mark are located, we actually have a pretty good sized facility here with a variety of manufacturing suites in addition to our warehouse and our labs, which is where I work. So it's been very nice to just walk down the hallway and we can see the manufacturing happen. We can collaborate and talk a lot more easily than having to kind of go to a different site to see what's going on. So an overview of the Charles City site. We have a variety of sizes of kind of manufacturing capabilities. So we have commercial scale, mid-scale, pilot plant, and a kilo lab. And with this variety of sizes, that gives us up to 350,000 liters of commercial capacity. So a very large manufacturing facility on site. In addition to our R&D labs for chemical development and analytical on site. We also have the ability for controlled substances and high potency compounds. And we have a strong regulatory history with a variety of regulatory agencies in the US and abroad. So we kind of work with a lot of different technologies and people, and that kind of makes it a very interesting place to work and get a lot of interesting projects. So to kind of get into what we're doing for this project we're going to talk about today, we had a process come in that was a biocatalytic process with the biocatalyst supplied by our Wiesbaden site, which specializes in biocatalysis. And so this is a pretty simple project from a chemistry standpoint. We just have a reaction in which two starting materials, A plus B, react to generate the desired product C and a byproduct that is volatile D. And so our challenge was to find ways to improve the reaction conversion. And so this is quite simple. If we think about Le Chatelier's principle, this is something we talk about in high school chemistry, if we remove one of the products, such as our volatile byproduct D, that will push the equilibrium forward, and now we have more of our C generated. And so even though this is quite a simple concept from a chemistry standpoint, what was interesting about this project was that from a practical side and an engineering side, this was a lot more challenging to implement. And the biggest challenge was the formation of excessive foaming throughout the reaction due to the sparge. We have a biocatalyst in solution that gives it a high protein content, and so has a high surface tension, and that just causes a lot of foaming when you start blowing bubbles into solution. And so this is when we really started working with our engineers to kind of figure out what might be causing this, how they might be thinking about this problem. And so with our engineers, they threw some equations at us, but for the chemists, basically what they kind of were thinking about is the characteristics that are going to lead to best mass transfer and removal of that byproduct. You want high gas flow, you want a high gas and liquid surface area, so small bubbles, and you want a long bubble retention time, typically through agitation, pushing the bubbles back down into solution. Now, if we think about the characteristics of something that's going to cause the most foam, you want a high gas flow rate, high bubble surface area, and long gas liquid contact time, such as agitation. So basically, what is going to give you the best mass transfer is also going to give you the most foam. And so we have two things in conflict that we need to balance. And so that's really where the challenge of this process came through, is balancing these two concepts. And so we decided to take a little bit of a more phased approach to developing this. And that first, we wanted to focus just on developing the sparge and find conditions that balance efficient mass transfer for removal of that byproduct and push the conversion of the reaction, while also minimizing the amount of foam we were generating. And then after that was improved, maybe we could go to changing the chemistry for targeting increased throughput. But first, we wanted to simplify by just looking at sparge conditions. And so again, this is where we really wanted to start working with our engineers early on to make sure that we have something that was conducive to transfer to a production facility. So for our initial experiments, our just first proof of concept setup was still an overhead stirred reactor, but we had a glass fritted sparge tube for our sparge, and we didn't have a way to control gas flow. We were controlling it by setting the pressure on our regulator, but we weren't actually measuring the flow rate in any way. We were just kind of uncontrolled, and that was what was leading to excessive foaming. So this is when we really started working with our engineers to figure out how to best build a sparge setup that would be similar to what they would be doing in production. And so this is when we kind of set up our second generation of a sparge setup. So the biggest change was a single point injection rather than our frit, which doesn't really have a directed stream. With the single point, we can direct it into the agitator blade so that it's most likely to be pushed into the vortex and kind of held in solution longer. And then also, because we were seeing that mixing was going to likely be a really important aspect of this, we wanted to make sure that we were matching the reactor geometry of the target vessel in production. So for example, we switched from using one agitator blade to two stacked on top of each other. We also installed baffles to, again, match the reactor geometry. And then a big portion of this was also the fill level. So previously we were only filling the reactor about halfway, but our target in production to kind of get as much out of each batch as possible, we'd be wanting to run it as full as possible, which doesn't leave a lot of room for foaming. And so we wanted to make sure that if we were running a reaction, we wanted to make sure that even if we had minimal room for foaming, we were matching what we'd be seeing in production. And so this setup worked out really nicely for us. It gave us a very nice proof of concept and early start to where we wanted to be moving in our optimization. But we started to have some issues with the use of the rotometer, which is what we were using for our flow rate measure. So these are very simple, analog, cheap to install, but there's kind of there's wiggle room of how you're reading it. So you have a ball that's floating on a scale, and you're just reading where that line is, and the ball is wiggling. So there's some wiggle of trying to average out where that ball is actually landing. So it's just kind of hard if you're trying to get an actual reading for something like a DOE or a data analysis. Additionally, with our biocatalysis in solution, we had a lot of solids, and this would cause the sparge tube to get clogged, and we'd have back pressure. And so we'd have to be manually adjusting the flow rate to achieve the flow rate desired. And so this was not conducive for, a 48-hour reaction. Someone would have to be in overnight to try to adjust. So we decided to switch to our next generation, where instead we installed a mass flow controller. So these are a bit more expensive, but are a lot more conducive for these kind of long extended reactions, especially if we had problems with back pressure. So these mass flow controllers have a electronic component with a feedback loop. So you will set a certain flow rate, it will open a valve to achieve that certain flow rate. And if it starts to detect a back pressure or the flow rate starts to drop, it will automatically send a signal to open the valve further to reach that new flow rate that was desired. So this was nice for making those automatic adjustments without us have to be physically in lab to observe it. And then the other part, since we have a digital output, we have a very accurate reading of what our flow rate is, and it can be attached to a PC or a computer system to be monitored 24/7 and record that data automatically. And so that's when we got really excited to use our LabOS platform that allowed us to do a lot of this data-rich experimentation. So what is our LabOS platform? So this was a data collection and automation tool developed at our Snapdragon site, and it enables data-rich experimentation and control across a variety of science instruments, so equipment that we're already using day to day. It allows us to remotely, so even if we're not in lab, or if we're at our desk in another room, or if we're off-site, we can view what is happening and monitor our experiments, and that allows us to, control it. But also, if there's safety features or automation that we want to control, we can do that as well. And so, what this kind of looks like from a more practical way of looking at it. So we have all of our equipment that we use day to day, from our pumps for flow chemistry, our circulators for our jacketed reactors, even something as simple as a J-chem for reading a temperature output. We can connect them all to a central server. And as chemists, then we can go in and connect each of the desired equipment to a given experiment through a notebook page. And so now all of that equipment for a given reaction or experiment is connected to a notebook page and starts to record all of the data 24/7. And that was really helpful for us, again, since we're doing long-term holds. It's nice to have that really precise data throughout that reaction. So kind of more specifics of how we use the LabOS for this project specifically. The foaming could be a little misleading because we would set up a reaction, we'd leave for the day. After about 4 hours, there's very minimal foaming occurring. You can see a little bit at the top of the reaction. We'd come back the next morning, again, very little foam, but we'd see scaling on the side of the reactors, maybe on the lid, that would show that something happened that we just weren't there to see. And so when we started recording with a camera, taking photos every 5 minutes, we can see a very clear picture of what happened overnight, even though we weren't there to physically see it. And so we see that the first 4 hours of the reaction, there was minimal foaming observed. And then something happens around the 6-hour mark where we start to see foam build up. And then at the 9-hour, we see a very excessive foaming. So this is a 1-liter reactor, and the foam filled the entire top half of the reactor. And then without any changes to the sparge or the agitation or anything, the foam clears and we come back to no foam at all. And so having the camera to track it allowed us to know what's happening, when do we need to be sampling to try to figure out what's going on with this foaming. So we were able to plan reactions and sample during this foaming period, and we found it's kind of corresponds to the 24 to 70% conversion. And so we think it's not from a byproduct being generated. It's as the reaction mixture, the species in it are changing as the reaction is progressing. It seems like that middle of 24 to 70% conversion is when you have the highest surface tension, and so the most foaming. And then as the reaction progresses, the foaming starts to go away as the surface tension changes. So that is kind of how we use LabOS to track our foaming, but we can also use LabOS for something like our mass flow controllers and the gas flow rate that we were observing. So here's an example of a gas flow rate. You can see our set, which is the straight line across, versus the kind of slight variation of the actual flow rate. That's this purple line over several days of a reaction hold. And of course, the disruption happens at about midnight on the 4th day of the reaction when no one is around to be viewing that and seeing what's happening. So when we had a reaction with low conversion, we were able to retroactively go back and troubleshoot what happened. And we were able to determine that this was, again, due to the solids in solution clogging the sparge tube. And while it was eventually able to overcome the blockage, it still was a period where we weren't reaching the flow rate that we had set. Another example of how we use the LabOS, if you're not doing something as, unique, something as simple as a temperature trace over a reaction hold can be really, really useful. And here we can see our set temperature of a jacket versus the actual temperature from of the circulator and our JChem. And so even for this reaction, it's not a very exciting trace since it's just a hold at a constant temperature the entire time. But you could see how if you were doing a distillation or a crystallization, this would be really helpful to have a detailed map of the reaction temperature over time. And it'd be really helpful for a data-driven approach such as DOE. And because this is our experiment and this is our equipment that we're using day to day, it's a low barrier to use. So every single experiment we're running, we're getting this kind of data out. Even if it's not necessarily helpful, it's always something that we have in case it is helpful later on and we can go back to it. So now that I've talked about kind of the tools we're using for this project, I can get into some of the development work and the data we were seeing. So when we started looking at our Sparge parameters, we started looking at a variety of conditions like the dip tube aperture, the delivery pressure and flow rate, the agitation rate. And so what we found was interesting is that the dip tube aperture didn't have much of an effect on the foam or the conversion. Whereas if we started looking at agitation rate, we see a really big impact. So even if with the same kind of conditions as far as flow rate, if we increase the agitation from 75 RPM all the way up to 800, we see a large increase in the amount of foam generated. But interestingly, we don't see any change in the conversion. So this gave us really good hope that there might be conditions where we see minimal foaming, but we are able to still reach that high conversion that we had a goal for this project. And so we decided to take a data-driven approach with optimizing this Sparge using a screening DOE to look at these parameters of agitation rate, our flow rate, and the dip tube aperture. And so for our conversion, the only parameter that turned out to be statistically relevant was the flow rate of the Sparge tube. Whereas for our foam height, kind of similar to what we were seeing with early experiments, was the agitation rate was the main factor contributing to foam height. And so with this DOE software, we're able to generate a sweet spot plot. So here it's generating a plot with agitation rate versus the flow rate. And we tell the software to kind of predict regions where we will have two conditions met: a conversion above 99% and foam less than 2 inches. And so anything in blue is conditions that give you one of those outcomes, and green is conditions where both of those outcomes are met. And so what we were looking for in our sweet spot between these two parameters we're trying to meet is something with really high flow rate, but minimal agitation rate. Which was a bit surprising for us, considering we have biocatalyst solids in solution that we need to keep suspended. We would think that the agitation would be really important, but it turns out that if you have this high sparge rate and that you need to be removing that byproduct, that's doing all of the agitation and suspension for you. And so any additional agitation is just causing shear, that's causing more foam and more bubbles and doing more harm. So this really helped us understand the kind of parameters of the sparge a lot better. And so this was all done at the 1 liter scale, and we wanted to observe how this scales up. And since mixing was a really important aspect of this development and of the outcome of the reaction, as we move from the 1 liter to a 5 liter, we wanted to make sure all the dimensions were scaling in the right way and keeping everything consistent as we could. So excitingly, with the 5 liter scale, when we scaled the flow rate volumetrically, we see that the conversion matches quite nicely and the rate of the reaction matches quite nicely with a 1 liter reaction. However, we were seeing a lot more foam generated at the 5 liter scale. So instead of 3 inches, we're seeing 18 inches, which is quite a lot of foam at this scale. And if we try to decrease the flow rate to generate less foam, we do see less foam observed, and the reaction does eventually reach conversion. It's just much slower than what is practical. It would take several days longer. And so this is when we kind of decided that if we are going to have conditions that remove that byproduct in a practical amount of time to reach the conversion desired, we're going to be generating foam. So are there ways that we can design in controls for foam as it's occurring throughout the reaction? And so this is where we had some fun getting a little creative of how we can design in engineering controls for foam, such as having an agitator blade or some kind of physical disruption in the headspace that would break up the foam as it was forming, or some kind of directed headspace stream of nitrogen that would poke holes in the foam as it's accumulating. Both of these turned out to be not very effective, but we had some success with this idea of a spray head. And so the idea was that we would have our reaction mixture recycled through a pump into a spray ring above the reaction mixture, and that would spray the reaction mixture down onto the foam and break it up as it's forming throughout the reaction. And so we had one of these fabricated for the 1 liter and the 5 liter scale. So you can see this picture on the right. We had our reaction vessel with a pump cycling the reaction mixture. And then the far right is kind of a picture look from the bottom looking up at this fabricated spray head to see we just had holes drilled that were dripping the reaction mixture down. And so this proved to be effective at controlling foam at the 1 and 5 liter scale, but we found that as we scaled up, it became no longer as effective because the foam production was volume dependent, but the elimination with the spray head was only surface area dependent. And those two didn't necessarily scale in the same way as we moved up in size of the batch. And so this is when we kind of had to reevaluate what we were trying to achieve. So with our second phase, we wanted to wait until we had the the Sparge optimized before we made changes to the chemistry. But if we're making changes to the chemistry, one thing we could add was an antifoam additive, which are very effective at controlling foam and would solve a lot of the problems we were having with foaming and allow us to achieve the Sparge efficiency that was necessary. And so when we started looking at antifoams, there's a variety out there. And so kind of give you an idea of how antifoams work. They are typically some sort of oil or insoluble or immiscible solid that sits on the surface of a liquid. And it is typically some sort of surfactant that sticks to the sides of the bubbles that are forming and weakens them. So they're more likely to pop before you have this huge pile of foam forming. And so this is quite a simple kind of concept, but very, very effective. So here are two side-by-side reactions with similar Sparge conditions. On the left, we have a reaction with no antifoam, where you can see the foam is filling the reactor headspace. Is not something you want to be running in a production facility. Whereas on the right, with 1,000 ppm of antifoam added, this is about a few drops for the 1 liter scale, we now have no foam at all. And so this was quite effective for us. And so we were able to start evaluating the chemistry more. And so through evaluating the chemistry, we found an interesting effect on the counterion of the acid used. So with one example of an acid, we found a kind of minimal change from 25 volumes of water down to 10 as we're getting more concentrated. But as we started dropping down to 9 and 8 volumes, a very significant change in the rate of reaction was observed. Whereas for another acid, we saw still a decrease in reaction rate as the reaction got more concentrated, but that decrease was way less drastic. And so we were able to run the reaction a lot more concentrated and still reach the desired conversion. And so what this meant for us is that now we're able to run the same reaction in the same volume or the same vessel and get twice as much product out. And so this helps us increase our throughput greatly. And so again, moving into kind of finalizing our optimization, taking a data-driven approach with a DOE analysis for validation enabling studies. We started with a screening DOE. So this is the kind of idea of a screening DOE is to eliminate factors from that are not going to be significant to the outcome of the reaction. So we did a risk analysis to determine that there were 12 factors initially that we decided might have an impact on the outcome of the reaction. And through the screening DOE analysis, we were able to eliminate 9 factors that were found to be non-significant. And so that left us with 3 potential critical parameters: the water volumes, concentration, the pH, and the flow rate. And so we could move into an optimization DOE. And so what this does is now we have fewer factors, so we can get a higher resolution model with fewer experiments. And the idea here is to get a really nice map of the design space that we can use to set our PAR and NOR ranges. And so you can see here's the map generated from our optimization DOE. We have our gas flow rate versus our water amount or the concentration. And so we can see any of the areas in green are predicted to have a less than 1% chance of failure versus red is increasingly more chances of failure. With the flow rate, we can see it's almost one-sided. As long as you are achieving a high enough flow rate, you are going to achieve the high enough conversion that we were desired. Whereas for the concentration of the reaction, it's kind of two-sided. So if we start to get too concentrated, we start to have inhibition of the biocatalyst. And if we start to get too dilute, now the reaction is slower and you start to risk achieving the conversion in the desired amount of time. And so this is where we can kind of set our PAR and NOR ranges of how much risk we're comfortable with and have a really nice picture of anything in the box is something that we are comfortable with running. So again, this was all developed on the 1 liter scale, and we wanted to observe how this is going to scale to production. So we started with a 5 liter batch again, scaling our volume by our gas flow rate by the volume. And again, we see that the conversion and rate of reaction is similar, but very minimal foaming observed. So this tells us that our antifoam was effective even at scale. And so with this promising results as we scaled up in the lab, we were excited to kind of continue working with our engineers to understand how this would be transferring to pilot plant and production scale. So I will hand it over to Mark to discuss that.
Thank you, Jenna. And I certainly want to thank Jenna and team for involving us in this process. It's been fun to get back into the lab and spend a bunch of time discussing how the engineering principles and such might interact with the chemistry. And this is an ideal type of project for that. I apologize that I will have to do this presentation camera off. I'm having a bit of a bandwidth issue, so I'm not able to project as well as speak at the same time. So hopefully we don't have the bandwidth issues. Please notify me if we are. Let's see, here we go. So what we did was we moved from our laboratory batch of 5 liter and 1 liter scale to a pilot scale, so about 225 times scale up in terms of our scaling factor. To give you a scale, a direct scale, but we were running about 1,100 liter scale reactor and running that at about 75% full. So the first thing we wanted to do was just make sure that things behave the same way it did in the laboratory. We looked at some of the same parameters we looked at in the laboratory. We built a sparging system or a gas injection system first that was the same that they had in the laboratory, which is, a single point injection. Certainly not your ideal way of getting small bubbles in the equipment. But what we did is we designed this single point injection to have the same velocity that we were seeing in the laboratory, scaling up the amount of gas we were injecting by volume, and then just making the port on the end of that to be to scale to the same velocity. Our first experiment was to just look at that and try to duplicate what we did in the lab. The second experiment, we designed a more classic style sparging. We call it a foot because our little hockey stick design here looks like a foot. So we designed a system that had multiple holes in it, again mimicking the same velocity, but that velocity now coming out of I think it was 7 or 8 holes versus a single hole, and looking at the effect on that on foam versus reaction rate. And the good news was, in our very first batch, very first 2 batches, we had pretty much identical success to the lab. Always good to see when all of the predictive models, I like to say when physics works, but it's always good to see that you can predict what you are going to do in the pilot plant. You do the same thing as you saw in the laboratory. And we saw no foam, and our conversion in the same amount of time that it took in the laboratory, maybe even a little faster in some respects, to be greater than 99% conversion. So very good effectiveness. Also did not see a huge difference between the 2 different types of injections, so gave us lots of flexibility in how we might do this. So one of the things we did understand, though, and we looked at this we saw this right away, the amount of nitrogen or gas that we are injecting into this at a 200-gallon scale is a lot. Our manufacturing scale is 4,000 gallons or 15,000 liters. If we scale directly to that particular scale with the same nitrogen flow, we're looking at 25,000 liters per minute of nitrogen, or more than 1,800 kilograms of nitrogen per hour, which out of a cryogenic system means we'd be filling tanks every day or every other day. And we would have to have evaporators on that system that would be extremely large, and we'd probably be making icebergs on the outside of them as we're generating our nitrogen. So we wanted to look at what are ways of reducing the amount of nitrogen we consume within the plant while still achieving what we wanted to achieve. And right off the bat, we looked at three things. So the first thing was to just reduce the flow, to see if we were getting a little higher efficiency in the plant than we were getting in the lab, and see if we could reduce our flow somewhat and accomplish it that way. The second would be to take a look at the nozzle design, try looking at even smaller holes, pushing things through at higher velocity. We didn't have a lot of hope for that, mainly because we went from the worst case scenario of one great big pipe to a multi-port design and didn't see a lot of improvement. The third option is to essentially make our bubbles bigger. So use the same amount of nitrogen, but make our bubbles bigger. That little engineering equation that you saw back in the beginning, what that tells us is that the amount of this volatile material we pull off per bubble or per volume is the same regardless of the pressure in the system. So as long as we have volume pushing through the system, we're going to generate the same amount, or we're going to remove the same amount of that volatile compound. So what we started to do was look at reducing the amount of nitrogen through, but drawing vacuum on the system so that the volumetric flow of nitrogen through the system was the same. And turns out that helped, that worked. So we looked at all of these different options. We looked at the increasing the or decreasing the nitrogen flow through the system at the same pressure, and reducing the nitrogen flow through the system at reduced pressure. And we saw that our conversion time was the same for the same volumetric flow through the system. So if we look at our nitrogen consumption, by just reducing the pressure of the system, we are able to reduce the nitrogen flow through the system by 3/4. So taking ourselves from maybe filling a nitrogen tank every 2 days to filling a nitrogen tank once a week, much more capable way of running the process. Also, that cryogenic nitrogen costs money. Adding a vacuum pump to a system is a single one-time capital cost. So we're doing that classic balancing of capital cost up front versus operating cost forever. And we have found through our pilot operations that we can run this process at a much lower continuous cost by investing a little bit more in our hardware. And I think that was the end of the pilot plant section. So Jenna, please wrap us up here with how much of an improvement we've made over this whole process.
Yeah. Yeah, so we were excited to see the pilot plant success. And again, with all of the changes to the chemistry, we were able to make a pretty good improvement to our overall throughput. And kind of wrap up what we summarized today, we were utilizing data-rich experimentation from our LabOS platform to support our studies in the lab. And we were able to design and optimize a subsurface sparge to remove a byproduct. And through working with the engineers early on, we were able to smoothly transfer from the lab scale to the pilot plant. And this really allowed us to study this at a larger scale, a pilot plant scale, that allowed us to kind of figure out what are the best conditions moving forward, especially with the use of vacuum to balance the need for nitrogen. So looking forward, we are preparing for small scale validation as far as how else we can use the learnings that we had in the lab. We've now started using LabOS on all of our experiments in the lab. So at least at Charles City, every single experiment we're running, we're using LabOS to track the data. But really interested in learning, in taking our learnings of LabOS and mass flow controllers with gas dispersion, where else we can apply that. For example, hydrogenations or drying of wet cakes. How can we kind of further use what we've learned here? And so I would like to take a second to thank the team that we worked with. It has been a lot of different perspectives and views coming in, especially through the ups and downs. So I have to thank Mark and the engineers for helping us as chemists figure out how to think about these very engineering principles, but also being willing to kind of work with us on understanding the chemistry as well. And that's really why it's been so successful moving forward. And so, yeah, I wanted to also thank everyone for tuning in and being willing to take some time out of your day to listen to us. We're excited to hear if you have any questions, and thank you for listening.
All right, thank you so much, Jenna and Mark, for that fascinating presentation. And now we will transition over to the Q&A. So the first question, there are other products on the market that are designed for automation and data monitoring for lab scale reactors. Why did you choose to use the LabOS platform instead of other options available?
Yeah, so we have some of those other kind of platforms we use in the lab as well. But with LabOS, since it's internal, we can kind of work with our computer engineers at Snapdragon to build anything that we need that's not already built in. So that's been kind of a fun aspect of being able to kind of optimize through that. It's also nice that we can use the same equipment we're using day to day instead of a more specialized equipment. So we're not having to, it's not like a one-off experiment, it's every single experiment that we're running. And then it's a lot more modular because we can then take what we've used at the 1 liter scale, we can also use it all the way up to the 20 liter scale, and you're not limited by the size of the reactor available with that as another platform. So it's just been a lot more modular in that way. But yeah, we also have those other opportunities as well.
Excellent. You found the use of vacuum to be useful at the pilot scale. Was vacuum ever studied at the lab scale?
Yeah. We also looked at vacuum very early on. It seemed like just vacuum wasn't enough to pull the byproduct out of solution. And at the lab scale, we started to see loss of our starting materials. They're not very volatile, but they're volatile enough that we started to see loss when we were using vacuum. Whereas it seemed like at the pilot plant scale, the vacuum wasn't as, I guess, efficient, or it wasn't as having as much of an impact. And so we weren't seeing that loss of starting material that we were at the pilot scale. So that's where the pilot scale was really interesting, in that we could study something that we couldn't necessarily study at the lab scale, but we could see it at this like intermediate scale before we moved to production. So yeah.
All right. On slide 17, how did the gas flow level affect conversion and foaming? Why was one of the parameters kept at a single value when the rest were a similar range of gas flow levels?
see if I can get to. So I think the change in the gas flow rate was the difference between using a mass flow controller versus a rotometer, and that we just, there's variation, and so we couldn't really say that's a certain that was set at a certain flow rate. So we just included the range to kind of capture that. Guess what was the second part of that question? Sorry.
The second part was why was one of the parameters kept at a single value when the rest were a similar range of gas flow levels?
Okay, I think that was that one. What was the first half? Sorry.
How did the gas flow level affect conversion and foaming?
So it seemed like we saw that as long as we were hitting a high enough flow rate, we were going to see high conversion. And the foaming, we saw minimal changes in it. It seemed like, yes, if you had a higher flow rate, you were going to see a bit more foaming because of basically your increasing agitation and shear. But we saw the biggest impact was agitation. So if we had a similar reaction that was also run at, let's say 500 RPM with half the amount of flow rate, we would see less foaming, but also less conversion. Whereas you can see that with this example of if we doubled the agitation rate, we'd see a lot more foaming. So it's just kind of hard to parse that out. That's why the DOE was helpful to see what, while there are small impacts, what is having the biggest impact, what is the biggest factor that's contributing to that observation of foam.
Okay, excellent. Did you consider using a sintered metal sparger, which should give small bubbles?
Jenna, I'm going to jump in on that one.
Okay.
If the question is about in the plant, where that is probably more applicable, because they did look at sintered glass sparger in the laboratory, which is not really a plant option. So if your question is in the plant, looking at a sintered metal sparger, we did consider it. There are a couple of issues, especially in a GMP environment, using sintered metal. The number one issue with sintered metal is keeping it clean. Getting it clean afterwards, and then keeping it clean. We tend to move from one process to the next process within our equipment, and there has to be full clean out in between that is analytically clean. And in order to flush the sparging system, so it's a real practical answer, but in order to flush the sparging systems or to clean the sparging systems, the best way to do that is to push liquid through at the end. And putting liquid through a sintered metal system is much more difficult, much high pressure drop. Also, in a system like this, we had the tendency of getting gunk growing on systems. We saw it in the single needle sparger in the laboratory. We were very concerned about it in the plant. You have these large protein-like structures in this process, and they tend to build up. And if they built up on that sparger, there really wouldn't be a way to remove them. So it's really about keeping it clean and practicality. Also, and then a third answer is at the velocity that we were pushing through this, you didn't need very small holes to get very small bubbles. With the exit velocity from the tubes or from the holes in the tubes, it pretty much guaranteed that the bubbles were going to break up as they came out of the sparging system.
Got it. Is there any issue with the removal of the antifoam during product isolation?
So we later on do distillation, so we don't have problems with carrying it forward, since it is a very like the antifoam is going to be polymeric and very high boiling. So we didn't have any problems with isolating. If we would have had a recrystallization or something, that would have been more challenging, but the distillation was perfect for removal. We didn't have to worry about that carrying forward or anything.
Would a filtered air sparge lead to unacceptable side reactions such as oxidation?
I can go there again. Yeah, more on, I'll give you the answer more on the practical side again. We have volatile and potentially flammable materials within this process. So we tend to stay away from air in our equipment in general for that purpose. We did not want to use air. We needed to maintain an inert environment essentially for safety's sake. I do not think that the air would have caused chemical problems, but on a much more on the safety side of things, we had to maintain an inert environment.
All right. And how was the foaming at pilot scale at atmospheric and reduced pressure? Was it comparable to the lab scale?
Yes. So we saw essentially no foaming. The antifoam knocked the foam back to the point where we did not really have to have that as a concern anymore in this part of the process.
All right. That's all the time that we have today for questions. Any questions that we didn't get to during the webinar will be answered by email. Thank you again to Jenna and Mark for that excellent presentation. And thank you participants for being a great audience, and to On24 for the technology and production services. And a big thank you to Cambrex for the sponsorship that made this interactive webcast possible. For information on the next edition of CNEN webinars, please be sure to check CNEN. And for CNEN webinars, I'm Alex Taylor. Goodbye.